Welcome to the VaNTAGe seminar. And we're very happy to be starting in the new year a new series on machine learning explorations in number theory. And today, for our first talk, we have Yang-Hui He, who will be talking about AI-assisted theoretical discovery. And Yang, is it all right if we record this talk?
Sure, no problem.
Wonderful. And everyone feel free to ask questions during the talk. Okay, Yang, please go ahead.
All right. Thank you very much for this very kind invitation. My background is not in number theory, but I've always been a number theory groupie. So I'm very happy that I'm allowed to speak in this very nice crowd. So I'm going to talk a bit. I think Rachel and Drew asked me to give a more generalist overview of how AI has been helping with theoretical discoveries, and then I'll mention some of the work on in number theory in particular, especially as actually joined with Drew. And this is vaguely based on this couple of reviews. One I wrote in 21 and one I wrote in 24 about how you can see how kind of evolved from machine learning explorations in terms of mathematical data to a more general view of how AI is helping us to do fundamental mathematical research. And I'm going to try to say, I will try to argue that there are three ways that AI is helping us right now in terms of helping us with doing mathematics. So where I'm going to go through them one by one. I'm going to try to say there's a bottom-up approach where you treat mathematics as a formal logical system, and top-down as a creative or intuitive art, and then meta-mathematics as a language. I know these words exist sometimes in philosophy of mathematics or philosophy of physics, and I'm not a philosopher at all. I'm just loosely borrowing these terms, and I hope to at least give you a flavor of what I mean by these three directions. So in the first direction, this bottom-up approach, which is where you build up mathematics from grounds up, I think more recently people like Terence Tao have called this co-piloting, and this is certainly a very important direction where mathematics is going. So uh, I guess, just in a historical context, the 20th century answer to Euclid, in some sense, in the foundations of mathematics, where you can axiomatize mathematics, really should be attributed to Russell and Whitehead with Principia Mathematica. And the reason that, well, I guess, which is itself a response to Hilbert's formalization program. But this famously, this was killed within 20 years because of Gödel, Church, and Turing, because of the incompleteness results. But I love this wonderful quote by my very distinguished colleague, Professor Kim, who is a number theorist. And he always says the practicing mathematician hardly ever worries about Gödel. That we know there are undecidable statements in mathematics, but of the trillions that are decidable, that's enough to keep us busy for now. So indeed, in another 20, about 2 decade interval, where this program was killed, computer scientists really took the lead in terms of trying to devise a machine which could prove theorems. So this really started in 1956 with this automated theorem proving paradigm. And the first serious attempt was the logical theory machine of Noah Simon Shaw, where they actually did manage to prove some sentences in Principia Mathematica. I have no idea how this machine was devised or what language it was written in, because this is very, very early days for computer science. Interestingly, you may want to note that in 1956 was also where the word AI actually first appeared in print. And that was the Dartmouth conference where AI was proposed, the words artificial intelligence was first proposed as a computational device. So now that was sort of 2 decade intervals of the 20th century. Where we are now, the 21st century answer to all of this formalization program is MATLib. You may or may not be familiar with this, so I'll just give a little bit of what this is. So it was launched. So as I said, this approved co-pilot, proof assistants really go back to the 1950s. But the important thing is that when the programming language Lean was launched by Demora in 2013, There are other ones, like the Cox system and, various other ones. But Kevin Buzzard, who is here in London, in fact, only who comes and visits our institute regularly, he says what fundamentally changed the community was this what he calls a great marketing scheme. So up to this point, um, people were formalizing things that were not at the cutting edge of mathematical research. So in 2019, Buzzard, Comlin, and Massad formalized prefactor spaces, which only a few years ago won Peter Schultz the Fields Medal. But because they were able to formalize this, they were able to actually convince the math community that this is something very much worth doing because you're formalizing the very frontiers of mathematical research. And then that really took off. And the Xena project that Buzzard really headed, and that was a 10-year program where I think Buzzard recruited hundreds of undergraduates and master's students all over the world, and especially at Imperial, to literally type in sentences of all of the undergraduate knowledge of mathematics, which is, I mean, it's a small fraction of what mathematics is, but it's a non-trivial fraction of what mathematics is. So in 10 years, that project is completed. And they hit the return button in 2023. And indeed, every single thing you've been taught at the undergraduate level is indeed consistent in this formalized way. So that's good news. Nothing has been inconsistent. And and then of course, and this really, together with Buzzard and more recent papers, were especially the ones the liquid tensor experiment that Peter Schultz was involved with Buzzard, and then in this Gowers Green Manners and Freddie Manners and Tau paper on the proof, where they actually came up with the proof of the Fermi-Ricci, the polynomial version of this conjecture, whilst they were formalizing this, really brought MathLib to the frontier of mathematical research. And I think Tao gives a very nice summary in this talk this public lecture in 2024, which I encourage people to watch online. So now it's a very vibrant community. Somehow, in the pure math community, we're beginning to appreciate Lean more than the other languages. Precisely as I said, because of all of the efforts of these really leading mathematicians. So in 2023, the Lean FRO was started, and what this whole community is doing, what this is of course you can see where it is. So we're trying to march towards auto formalization. We're still very, very far from just taking a LaTeX paper and then just hit the button and translate that into lean code, or take whatever proof you may want to automatically. I think it's the hurdle is mostly actually technical in the sense that there haven't been enough lines of lean code out there for you to auto formalize. Nevertheless, there been small progress even within even last week. There's been this auto formalization by this paper where many lines of topology were auto formalized. And Kevin is currently hiding in his basement, he says, or attic, trying to formalize Wallace's proof of Taniyama Shimura. So this is certainly another, add a huge chunk of data to the arithmetic geometry community. And something that's also that's closer to my old background is Joseph Tooby Smith has actually done a physics version of Lean, where mathematical physics, which is my original background, where you wouldn't think that this is possible because most definitions in physics are very vague, but nevertheless, you can pick enough interesting definitions in physics that are not so vague, like Hamiltonians or symplectic vector spaces, and even supersymmetric algebras, and formalize that. So currently, since 2025, we've been running this the LLM, which doesn't stand for what you think it stands for. For us, it stands for the London Lean Monthly, where it alternates between these three institutions, um, where we meet once a month to do this to formalize more. I'm not a lean coder myself, but I keep a keen eye on what people have been doing. And indeed, just to emphasize that DeepMind's alpha proof, versus earlier versions of AlphaGo and AlphaGo 2 actually is beginning to incorporate lean code itself. So you can this is more trustworthy in terms of coming up with correct proofs. So that's the bottom up direction about of building up mathematics. This is certainly very, very important. And I think in some sense, at scale, AI's involvement in this bottom up approach has only really been the last year or so. So the next one is something that I guess I've been more involved with, which is this top-down, this intuition-guided mathematical discovery. And in some sense, this is just experimental mathematics on steroids. So um, if you think about, how we actually do research in mathematics, and certainly this includes theoretical physics, theoretical physics has never been a process. It has never been a bottom-up process. There's never no physicist ever starts anything with a definition. It's all these very vague definitions, very vague ideas and intuition. So here, there's this wonderful quote of Arnold, where he says mathematics is a branch of physics where experiments are cheap. And that's certainly true, where in theoretical physics and in pure mathematics, our data comes for free. We don't, well, free in the sense it's long up to computation, up to compute. But we don't build machines like CERN that cost 20 billion. And so this vaguely goes under the rubric of conjecture formulation from mathematical data. And I like this. My friend Mike Douglas, who is I think also a near where Jew is at Harvard, and I think this term first came from him. He likes to call mathematical data Platonic data. This is to distinguish yourself from experimental data where there's a lot of statistical error or measurement error. This is up to correctness in your computation. It has no statistical variance of any type. It's like think sequences of primes. I know there's no variation. So this is a very special kind of data. So so if you think about how so I certainly I will give you some highlights in the history of in the history of mathematics across the 3 centuries, and of course in this particular community of number theorists are particularly familiar with this kind of experiment. So like in the 19th century, Gauss was able to just look at this plot of the prime counting function and say this is x over log x. I mean, it's a little more complicated than this, right? Because I think Gauss actually had to invent regression and most of statistics in order to do this idea of best fit. But this is the interesting thing is that the first proof of this fact, not the one by in the 20th century, the first proof had to use complex analysis of Hadamard and Delavier-Poisson, and then a complex analysis was not a tool that Gauss had. So it's kind of very interesting that the formal proof um, came much later than this intuition guided thing. And of course, the BSD conjecture was the highlight of 20th century experimental mathematics. And again, it's a problem in number theory. And really, I think I was told that, BS and D were hiding in the basement with ETSAC computer at the time, and they were just making plots of ranks and conducted through the curves, which came up with a conjecture. So it's interesting that this is something that, I always emphasize to non-mathematicians is that 1/3 of the remaining Millennium Prize problems, namely the Riemann hypothesis, the BSD, actually came from experimentation. Riemann by hand plotted out like the first 10 or 20 zeros, and as a footnote, he remarked that I think they all lie on the one half line. And so this is kind of very interesting how intuition guided mathematical experimentation is a very much a formative part of what mathematics is. So then, now how did I get into this idea of using AI or machine learning at the time to do this kind of exploration? Well, my background is in the interface between algebraic geometry and string theory, and one of the I'll give a little bit for this community just see where this problem comes from. So basically, in algebraic geometry, there's this famous classification theorem, which basically says that in complex dimension one, there's this trichotomy that this Euler classification, the topological classification by Euler of genus and Euler number, follows this vague uh, trichotomy in the sense that they're the positive curvature of the sphere, well, later realized to be actually a complex surface. So the positive curvature of the Riemann sphere, the zero curvature of the torus, and the negative curvature of surfaces of general type. In this case, complex curves of general type. So vaguely, these are Fano varieties, Calabi-Yau varieties, and varieties of general type. And a lot of the work in modern geometry is to extend this trichotomy, and to in particular relate the curvature of these objects to some version of index theorem, or some kind of integral, some generalization of Gauss-Bonnet formula. So it's kind of remarkable that the how this was there's almost 3 centuries of progress since Euler in just trying to generalize this diagram. And by the 20th century, and the general problem is extremely difficult and it's still not known. And in fact, much of the minimal model program is to generalize this direction. In particular, when your variety is scalar, in the sense that your Hermitian metric comes from a potential, Calabi famously conjectured in the 50s that essentially this diagram does indeed generalize, and that the Chern class controls the curvature in this sense. So in particular, the vanishing of the first Chern class is indeed equivalent to the Ricci flat. So condition. And now, Calabi already showed that the uniqueness of the existence of such Ricci flat metrics, or in general Ricci curvature being controlled by the Chern class, but he didn't have an existence proof, and that had to wait for Yau, who immediately got the Fields model. So you can appreciate how important this problem is to generalize this diagram in any way you want. So now we have a good control, at least, of this thing for Kähler varieties. But in general, it is still a very much open problem. We don't even know how much. It is a theorem that for Fano varieties, the positive curvature objects, there's finite type in topology. It's still a conjecture, open conjecture of Yau, that the Ricci zero case is finite in topology, and we know that this is wildly unclassifiable for varieties of general type. Now, very remarkably, why are physicists interested in this? And so in 85, there's this famous paper of Candelas, Horace, Strominger, and Witten, when they were just trying to compactify superstring theory. There was a 10-dimensional theory, and we live in this 4 dimensions. And this extra 6 dimensions, one of the solutions they got for this 6 dimensional extra dimension was actually Kähler, complex, and Ricci flat. So the physicists didn't know what it was. What are these conditions? So they wrote this out in these horrible coordinates. And Strominger was actually visiting Yao at the Institute of Advanced Study right around about 85, 86. And Strominger went to Yao and asked, what are these? What kind of metric does this solution for a superstring vacuum actually describe? And Yao says, I just got the Fields medal for this. I think I know a few things, one thing or two about these. And these are called Kähler manifolds with Ricci flat curvature. So indeed, it was actually the physicists who then named these manifolds as Calabi-Yau, in honor of Calabi and Yau's proof of the Calabi conjecture. So the word Calabi-Yau actually first came about from the dialogue with the physicists. So for our purposes, Calabi-Yau basically stands for roughly smooth, compact, Kähler varieties with vanishing first Chern class. And somehow, these things pop up everywhere in physics. They show up. These Claviel varieties that have nothing to do with string theory. They show up in the supersymmetric standard model. They show up in ordinary 5 to the fourth Feynman diagrams. It's still mysterious why this kind of Ricci flatness condition actually show up, but it's a thing. So the crazy thing about Claviel manifolds is that in complex dimension one, there's only one example. Basically, the topologically it's just the torus. In dimension two, there are two of them. There's the four torus, and there's the K3 surface. In dimension three, unfortunately, we have no idea how many they are. It's a conjecture of Yau's that there's a finite number of these in topological type, but we don't know. It's still open, and Yao, in fact, conjectures that in every complex dimension, the number of Ricci zero, this Ricci flat objects, is a finite type in topology. We know it is a theorem for positive curvature, the Fano varieties, but the zero ones, we don't know. It's a best hope scenario if it's finite in topological type as well. So the physicists, but nevertheless, physicists now have done. There's been a lot of work over since the mid '80s until recently by Candelas and Delos and many people in conjunction with algebraic geometers to just start classifying these objects. And we've gotten, I won't bore you with the reason for this, but we've gotten tens of thousands to half a billion of these manifolds now on computer by the turn of the 21st century. So how I got into this was just, I had the data of these varieties. So the typical computation in algebraic geometry and in particular in string theory is to take one of these varieties. Here, I'm not going to bore you with how I represented this variety, but this is just as Vanishing, say, for example, Vanishing loci of multi-degree polynomials. Each column is some multi-degree polynomial embedded in projective space. So this is one way to do it. You can embed it in Grassmannians or toric varieties as you wish. And then you chase sequences to compute some kind of topological invariant, right? So this is getting a matrix, and there are standard methods to do this. So the standard method is to just chase sequence and to induce sequence non-exact sequence cohomology induced from the early sequence. But the actual computation of this is very expensive. And the basic reason for this is that whenever you run into some kind of algebraic variety, you're stuck with the fact that the complexity of computing the Grobner basis is a double exponential complexity problem. So it's by a tour de force over 40 years that algebraic geometers and physicists have joined forces to compute these topological invariants for these using various techniques. So what I did back in 27 was just to train a very baby forward feed neural network to just try to predict this. And the way that I fed this in data was to pixelate such varieties into, say, for example, one is green and zero is purple. This is completely nonsense in some sense in the mathematics. And I didn't expect it was going to be able to predict this topological invariance at all. I was just treating this as basically as a training a handwritten digit recognition problem. To my complete shock, that it was doing very well, and now it's been various people in the community have increased the accuracy of this. You take a set, say 100,000 to 200,000 or a million varieties of such a type. You label them as pictures, and you label them with whatever topological invariance. This is a Hodge number. And you say, I'm going to train 20% of them. I'm going to start predicting 80% of them or whatever, 50% cross-validation. And you get 99.99% accuracy. Now, this is good news in the sense that neural networks is kind of doing some pattern recognition, which is good. It's bad news in the sense that we can't extract any meaningful mathematics from it. We have no idea what it's doing. But nevertheless, there's some underlying structure where it's doing something. So how have we improved from this in 9 years is something I'm going to comment now. So, nevertheless, what I became an avid convert to machine learning, and back in 2017, and then I started saying fanatical things like, all of algebraic geometry is just image processing, and I haven't been shot when I give these talks. So I think, in some sense, a lot of people agree with this rather radical statement that that algebraic geometry is image processing. I mean, oh, indeed, at some level, all of mathematics is image processing at some level, because you can always consider something as a Turing machine, and then you can pixelate whatever information you want. Now, so since 2017, I've been making lots of friends. So I can't put them all of the name. Just trying to get platonic data from every branch of mathematics that I can from every friend that I can make. And I'm extremely grateful to my very talented students who have helped me in just making new friends. So I think indeed probably the most the only thing more fun than doing mathematics is making friends while you're doing mathematics. And well, anyway, this a lot of this is recorded by into this editorial, and then this book on the Calabi landscape from machine learning. What's interesting, you can see that here's a plot of the number of occurrences of the of variants of the word machine learning, AI, deep learning, neural network in abstracts and titles of papers in across different archives from 2017 till now in fields that normally would never have such a word. And you can see that this is very much a growing field. What's interesting is the GRQC, so that's the quantum gravity general relativity crowd. This one has actually the most usage, most growth rate, and that's because a lot of the GRQC community they do numerical general relativity, so the machine learning inevitably helps them to do it. And number theory is somewhere over here, but there's certainly an increasing number. And HepTH is another community. The theoretical physics community is also very much taking on in how this is doing. Of course, this is a very rough diagram, right? And I didn't include all of the possible words that so this is a slight underestimate of the number of hundreds of papers that have been appearing as a growing community. Indeed, there is so I'm very happy that Drew and Rachel and Drew are doing this theme for the VaNTAGE seminar, because there have been an increasing number of annual series of that basically go under the AI for math. So there've been ones, the string theory community was the first one to really pick up. So there've been annual conferences on string data. And then there's the danger series. That's the one I was mentioning to Rachel, which was also an acronym. It stands for Data in an Analysis, Geometry, and Representation Theory. And then there are various ones. NeurIPS now has representation of this group in AI math, and then Douglas runs one. I think Drew runs another one. Yeah, so this is indeed there are various ones that are growing that are dedicated to this AI for math paradigm. So you're bearing that in mind, it would be nice to have an idea of what constitutes a fundamental AI-led discovery, at least especially in the context of raising a good conjecture, right? So remember, in the three directions, bottom up is basically finding a good proof. Top down is basically finding a good problem. Um, so in 2022, ChatGPT passed the Turing test, and um, in 23, I was organizing a conference in the Isaac Newton Institute with a bunch of collaborators. So this is it's a big conference that lasted for 3 months, where we try to get all of this, as many of these friends that we could get into a single room across different disciplines of theoretical physics and pure mathematics to just have a dialogue. And one thing that came about in this dialogue was this idea of what constitutes a good conjecture made by an AI system, and sort of in response to ChatGPT passing the Turing test, and part in as a tribute to Brian Birch, who certainly was a very good at raising a good conjecture. We named it half jokingly this as the Birch test. So the Birch test basically is AIN for AI, where A stands for automaticity, that it has to be generated by AI. It has to be interpretable in the sense that you having some neural network spitting out some good answer in a good fit. It's not very useful to a working mathematician. You need a concrete thing to actually work on. And the N stands for non-triviality. So we've certainly reached the point now where the automated systems can raise conjecture. So this is something, for example, that's done by my friend Challenger Mishra at Cambridge, where you can raise hundreds and millions of conjectures a second, and many of them would be correct, but not very interesting, like things like 5 plus 7 is greater than 2. So it has to be non-trivial enough for the community to actually work on it. And but probably the most important aspect of the Birch test is that you actually have to make Birch happy. So I think, to my knowledge, in this in the strictest sense of the Birch test, nothing so far has really passed the Birch test, but we have come very close over the last few years. So the first example that I can think of is the famous paper of DeepMind, this DeepMind collaboration, where they did things everything from Kashtan-Lusztig polynomials to knot invariants. Now, this one failed the end test of the Birch test in the sense that they did indeed get using saliency tests. They inched out a new formula for a Jones polynomial, but they were able to prove them themselves as they went along. It didn't ignite activity in the field. Um, and then the same year we had this. So this is when this is when I realized that I've exhausted my knowledge of number theory. So I actually had to join forces with card-carrying number theorists, and first with Lee, Oliver, and Posniakov, and then with Lee, Oliver, Posniakov, and Drew. And then this is the memoration conjectures. I think I've seen from the upcoming series there will be people who will be talking about memoration conjectures. So I won't belabor so much here. I mean, it was literally just uh, mucking about in this, and I'll come back to the memoration in a minute. And this one, it fails the A test because, in the sense that when it was first noticed by us, and in fact, it was first noticed in computer form was done by Alexei Poznikov. It failed the A because we had to muck around. We had to choose our algorithm. We weren't at the point where you just literally fed in LMFDB, and then you would just say, hit the return button and say conjecture, just raise it. So we were constantly choosing our algorithms. We started with simple neural networks, and we did a tree and a tree classifier, and then we finally settled down on a PCA, a principal component analysis, which led to the actual concrete form of the conjecture. So more recently, in 2025, DeepMind has been recruiting the world leading experts in Navier-Stokes, and there have been increasingly very exciting papers, on Euler type equations, and then hopefully Navier-Stokes, in discovering new types of singularities for these particular types of PDEs. And again, to my knowledge, this is not entirely automated in the sense that you can just feed in the definition of Navier-Stokes and you will start trying to find it proof, or feeding in data that come from Navier-Stokes and you'll start to notice new patterns. More interestingly, and this has been a controversy that's going back and forth in the last week or last month or so, is how harmonic math is Aristotle system has been trying to crack Erdős problems, these particular Erdős problems. And they claim zero intervention, but now I actually I don't know what the status changes every week. To my knowledge, it could be the case that a weaker version of the Erdős problem was fed into Aristotle, and or that Aristotle has actually found some existing literature which imply this weak version of Erdős. So this is still an ongoing process to decide how much does this pass the Birch test. And of course, this idea of raising conjectures really good. I mean, graffiti was doing this for graph theory and TX graffiti for decades. And but it's only I believe that it's only recently that the TX graffiti system is beginning to incorporate machine learning algorithms to do this. So this is still very much an exciting field to get into. So this memoration, as I said, I won't talk too much about, and I think that was a nice quanta feature where you see happy pictures of all of us in here, and including Lina Trbylina, who actually was the first person to give an actual concrete proof of part of these conjectures. But something that I want to mention about the memoration conjectures was the fact that I did something very, very naive um, in this when back in the day, right after arithmetic geometry, after my experiments with Clavier manifolds, I did a work on try to machine learn the MLFDB, basically trying to predict rank. And this was done with two data scientists back in 2019. And I say this story because this is one of the reasons why it also fails the A test. So these guys are not mathematicians, and I'm not a number theorist. But because I came from an algebraic geometry background, I was trying to predict rank using the Weierstrass form of the elliptic curves. And you can imagine we didn't get anywhere, right? Because for an algebraic geometer, the Weierstrass representation of elliptic curves was the natural one. But it was only joining forces with Leon Oliver and Poznikov in 2021 that we realized that the correct representation for this curve for to get arithmetic information was the AP coefficients. So it's kind of interesting that you need a human expertise in order to guide where you're going with this kind of experimental data. So for just to put it out there, there's a lot of Platonic data out there, and this certainly is a very fertile ground for exploration. There are terabytes of freely online available data. So if you want to muck around with finite groups, you go to GAP, algebraic geometry, you go to the GRDB or the Clavier databases. In number theory, of course, is LMFDB. Knot theory, Snappy. So, and I think it's a fantastic thing for the community. I think that mathematicians are putting all of this freely available online for any kind of exploration. And we've only really touched the tip of the iceberg in terms of true AI explorations in raising conjectures from this. So, for example, there are 10 million groups in here, and we haven't really done much of it. Snappy is what led to the DeepMind paper to conjecture their Jones polynomial result. And then LMFDB, of course, is what led to the memoration conjectures and stuff like this. And the GRDB and CY databases is what led me to do the first machine learning explorations of algebraic varieties. Um, okay, I mean, I will skip this bit. I mean, of course, this is a wonderful quote in the sense that if there's one thing that AI can do better than humans is pattern detection. And and I won't bore you with this, but certainly one thing that's been always in the back of my mind is can there exist an AI algorithm that can predict um, uh, here the Liouville lambda function? Well, I don't know. So far, nobody's been able to find one. It would be very interesting if we did. And for this community, particularly for the arithmetic geometry and number theory community, it will be very nice. And it's kind of interesting that taking this sequence, just the parity of prime factors up to multiplicity, was actually one of the early challenges that Peter Sana gave to DeepMind way back in early 2020s. And I don't think DeepMind made much progress with this. They have all the compute in the world, but they didn't. I know the idea is to just predict the next number, whether it's zero or one, one for even and zero for odd, with something even slightly better than 50% accuracy. And I think that's an extremely important thing to do. Uh, so now let me go into the in so good. So there the talk has been divided into three parts, so they're 20 minutes each. So in the last bit, so this is really the mysterious one, right? So I talked about a bottom-up built-in mathematics where you use proof copilots building up on the library of Lean to try to formalize all of mathematics. And then then mathematics essentially becomes a game of finding a right path within the math lib, or to create. If you can't find it, then I know it's an infinite search space, but if you know imagine some reinforcement learning environment where you're trying to find the best proof path. Then, if it's not there, try to construct new sentences in mathematics and see where it goes. So that's the bottom-up approach. The top-down approach is where you try to take Platonic data, broadly defined, and you try to make new conjectures for problems to actually work on. So these two were certainly, they're contrasting directions. The third direction is this very mysterious one, which I believe a huge number of us are very actively engaged in, because in the sense that I think we're beginning to, on a day-to-day basis, interact with ChatGPT, not just to complete, to fill forms. We certainly do that. All the boring stuff is not taken over by ChatGPT, but to actually um, interact with ChatGPT to get responsible and correct mathematics. Now, this is entirely mysterious in some sense because LLMs make all kinds of nonsense, right? They say all kinds of hallucinations. How can you possibly get anything rigorous from it? Well, in this direction, let's again, this is a very rapid thing in last 2, 3 years, right? So 2022, as I said, was the passing of the Turing test. And then there were early versions where DeepMind launched its fun search, and Meta AI's Llama system read in all of the archive. And then 2024 is DeepMind's AlphaGeo and AlphaGeo 2. And the 24-25 range is where AlphaProof starts to incorporate lean. So it's a quite rapidly growing field. And so I guess, in some sense, July 2025 is approximately when this is the kind of stuff that get into headlines, is that AI is approximately equal to the 12-year-old Terence Tao, right? If you can reach the 16-year-old Terence Tao, then you're really doing cutting edge mathematics. So why do we say this? It's because I think by July 2025, AlphaGo 2 was able to get the silver medal and then a gold medal in solving Euclidean geometry problems. And I think now more generally, it's been recently marked that you can handle problems of such a nature very well. And and now, more recently, with Axiom Math, I think Kenono is involved in now. In fact, Kenono moved to Axiom Math precisely to do the next level, which is Putnam level. But of course, these are competition level problems, and competition level problems are very they're of a certain flavor, and there's a lot of training data for it because there's a huge international enterprise, right? It's that high school students are they've been abused as children since their age of 4 to be drilled to do this kind of exams. So it's a very specific type of training data for mathematics. So, but what about research level math? And so, indeed, to answer this, when in 2024, when DeepMind got the silver medal, it became clear that something should be launched to do research level mathematics, what we actually do, right? So that's when OpenAI funded Epoch AI, which is Epoch AI is a benchmarking company for AI benchmarking company, and then OpenAI funded them with this project called the Frontier Math Project. So as of this, then you give it advanced problems and to see how far it is problems of various degrees of complexity, right? So it was only when it was first launched in the summer of 2024, it wasn't doing very well. It was doing like something like 1% to 2%. And they thought that these problems would be safe for at least 5 years. But by December 2024, they realized it was actually already getting to the 25% range. And so by March of 2025, so you see how rapidly it grows, they completed their tiers 1 to 3 problems. So by tiers 1 to 3, they vaguely can think about, the benchmark here the math Olympiad for of AlphaGeo and AlphaGeo 2 are high score, extremely hard high score problems. Tiers 1, 2, 3 is vaguely first year, second year, third year, or early PhD level math problems. And then tier 4 is what you would a problem that you would give a colleague to or write a paper about. And it's a collection of approximately 100 questions to each tier. Um, so Ken was one of the early people to be involved in tiers 1 to 3, and I was involved in 20 in May of last year for the tier 4 problem. I'm going to give you an example of tier 4. So tier 4 is again tiers 1 to 3 is above high school. Tiers 1 to 3 is about to up to early PhD level. Tier 4 is the kind of problem you would give to a colleague or to actually work on. And indeed, it was commented, when they locked us up in the Berkeley HQ of Frontier Math. Um, some of us admitted that we're sacrificing a paper that we could be writing to do this because these are problems that are certainly they have no, to our knowledge, no prior appearance of any type in the literature. So these LLMs can't really start doing this scraping of literature. So by October 2025, 10% of these tier 4 problems have been solved. And now we're also up to the 25% roughly range. So just to give you an idea of this kind of problem. So here's a problem. I think this was actually due to Ken. They're of a specific type of problem where you phrase it in a very technical language such that the answer has to be a very, very long numerical answer. Here is some, 50-digit integer, or it could be like a 50-digit real number. The reason that this format was chosen was because sure, I mean, ChatGPT spits out proofs, but nobody's going to sit around and check through them. It's just not enough time to check it. But if your ChatGPT gives this answer, then there's no way it's going to get this by just random guessing. And we know that such numbers have also not appeared previously in any literature, so you can't do a search. So it has to be a problem of this type. So here's one by I think this one's by Ken, and I believe it has actually been solved. And you literally just type this into the various professional versions of LLMs, ChatGPT Pro, Claude, Gemini, and it was actually able to get this number by just reading this question, right? So it's just quite impressive, right? So in terms of you can see you can go to this website. I won't try to click on it because I think it'll just send. I don't want to touch anything. But please go to this website. You can see how different models, LLM models, performed with respect to problems of such a type. The problem that I gave was in algebraic geometry. It was just a very technical. Only there's really if you're looking at this kind of problem, there's really not that many people on the planet who would understand what this problem is. So it's a quite technical problem, and ChatGPT was able to actually get this kind of answer. So this is kind of interesting. Why is able capable of doing this, right? So here's some, like if you think about, what we've been taught all our lives, we've been taught the standard methods of proof, right? Proof by contradiction, induction, syllogism, whatever. But in practice, we also have various other methods of proof, right? We prove by intimidation. This is what professors use all the time. Authority, citation. And I love this word. I think I first learned this from Kevin Buzzard, which is proof by vibe. And then basically what LLMs have mastered is proof by vibe. And also, of course, proof by citation and by authority. And what is really interesting is because clearly, and I mentioned it just to go back again, since 2023, we already have all of archive in some version or another in some LLM. So, and it's remarkable how these LLMs, whether you want to call it or not, it's purely a philosophical question that I don't want to get into. I don't have a comment on it. But what I do know is that in practice, it could find things which are quite remarkable. So just as an example, which like say my friend John Duncan, who's an expert in representation theory of the monster, just last year, when we were just mucking around with this sort of thing. he was asking me a very, very specific question to type into ChatGPT. And it was a question that it didn't appear anywhere in literature. It has something to do with a particular conjugacy class of the monster and about the certain length of, I mean, I can't even remember. It's technical enough that I don't even remember what the question was. And the reason I mention this anecdote is that he then asked all of his close friends in representation theory, all the old the old school of finite group theorists, and none of them knew the answer. And they went and computed and they got an answer. And then ChatGPT, when we asked ChatGPT, it started to hallucinate, gave all kinds of wrong answers. But then after a few prompts with John, it gave the correct answer. And but what is remarkable is that it found a paper and it gave a precise reference to theorem 3.2, whatever it was, of that paper, which implied his result. Now, this is very remarkable because John didn't know that paper existed. The paper had zero citation. It's somewhere in Math and Science, and nobody's ever read that paper. And neither the abstract nor the title mentions anywhere any of the keywords that John was after. And yet, by whatever vibing, if you call that reasoning, it was able to actually deduce somehow that the theorem, whatever, of this paper, a corollary of this fact, immediately led to the answer that John was looking for. And this is now becoming more happening more and more frequent. In some sense, it's very difficult to beat this in terms of proof by citation, right? So to wrap up, and this is something I'm trying to tempt all of you guys. So this is where I am. So now you can see where I am in my office. Where this is, we are the UK's only independent research institute for mathematics. And we are situated in this floor. So this floor is now our institute, which is the floor that Faraday and the likes of Faraday and Humphrey Davy lived. And we've brought science back to this ancient and august institution. And so that's our entrance to the second floor. And what what we now do is one of our four themes is of what we do as a mathematics institute is AI for mathematical discovery. And the Nebius, which is an AI company, has just launched will launch next month a series for AI for theory, and we're going to have various speakers. And importantly, another AI company called Cognia has just given us money to fund two fellowships in the direction of AI or the theory of AI or AI for theoretical discovery. So just to wrap up, in some sense, you can see top-down mathematics as an image processing problem, and a bottom-up approach to mathematics as a natural language processing problem. And meta mathematics, LLM, somehow links in this in a mysterious way. And I think it's certainly transforming the way that we do research. And perhaps the future of mathematics is really the following kind of flowchart in terms of how we actually do research. So here, the human, I'm putting perhaps the epitome of the human mind. So this is, I think, the 20-year-old Terence Tao. You have papers coming from the archive. It will be digested by human and AI in some combination, where a top-down mechanism will give you a problem, a conjecture formulated from Platonic data that comes down from this, and some kind of auto-formalizer will then kick in. It will formulate these problems in MATLAB, and then it will go to a MATLAB environment and look for a lean proof path if it finds it. And if it finds it, it will then be digested by humans again, I think, because I mean, otherwise, having a couple of 100,000 lines of lean is somehow less satisfying than to actually know what the chunks are actually doing and fitting that together. And then this human will then write the paper, possibly in conjunction with an AI system, and then feed this paper back into the archive. So this kind of flowchart is clearly where we're going right now in terms of mathematical research. So With that out, thank you very much for your attention.
Thank you. Well, would anyone like to ask a question for this really interesting talk? Crystal, would you like?
Um, Thank you so much. This is a really interesting talk. I was wondering, in situations where there's a shortage of data, so there's some mathematical problems where you just don't have a lot of data, and say you're using an LLM, how has that been done in the past? Thank you.
Yeah, good. That's a good question. So a lot, sometimes we actually have to create the data ourselves. So for a lot of the experiments that I did, for example, like so create artificial data. So for example, in this, well, I'm trying to find the do here. So in these experiments that we did with Pierre de Champ, where there was just explorations of say quiver data, we actually needed to create more quivers of a particular type, or cyclic quivers, and there's no available database to this. So half of the work, or 80% of the work, was actually just try to generate that data. And then once it's generated, you can use some machine learning algorithms to try to detect patterns. So I think it's very important to get as much mathematical data, Platonic data, as possible out there. And I think this is becoming more and more of a standard practice where you, in fact, submit paper to archive with a link to GitHub saying where your data is. And it will be very nice to have this in a centralized repository in all branches of mathematics. But that certainly is a very important problem, a question.
I have a question it's not very fully formed yet, but how do you in your own mind, where I'm sure there are hundreds of things you can do, and how do you decide what you think is most important in terms of the next couple years with your interactions with AI?
Yeah, I think everyone is now working on, like, I think more and more of the mathematical community will be convinced if there's a big major conjecture or open problem that humans have not been able to crack, gets cracked. And I think that's why DeepMind is focusing so much of his energy on Navier-Stokes, because I mean, I'm certainly by no means an expert in PDEs, but just we're talking to people in PDEs. A lot of Navier-Stokes is about some kind of optimization, finding the right region with the right properties. So if it has you get a gut feeling that this seems like a tractable problem. So I think I would not be surprised if in the next couple of years, or fingers crossed, that DeepMind announces, a Millennium Prize problem cracked, and that would be quite something, and that would be a great, marketing strategy, and I think probably the most important for all of us to work on as a community is to try to see, because there are loads of them. This is why I think the Erdish problems have been so good in terms of benchmarking, and I think a lot of it actually been fed into Alpha Evolve to see which ones that can be solved. And that's, it's just kind of, as of course, the Irish ones are very, very technical, and not all of them are important. But it will be important to put we should just gather all of the important conjectures and try to see. And again, this requires experts, because experts have a gut feeling of which ones are likely to be cracked first, and then see whether LLMs, either by whatever method, if it finds obscure references that nobody's ever read, to it kind of hallucinated this missing step. I think they would all be great. But the most important thing is, once it spits out this thing, we actually have to sit down and actually go through the proof. Either if the if going through the proof by hand gets too complicated, then definitely try to find a formalization in MATLAB to check it. And these are all very important things. And these are standing challenges that we must address.
Yeah, thank you.
Sure.
Would anyone else like to ask a question?
Yes, I have just one question. Mm, do you think like in 5 or maybe 10, 15 years we can reach situation similar to AlphaZero when basically uh, machine can find a proof, maybe in Lean, long proof, but using its own mathematics, not really using our concept, and it will be very difficult for humans to understand this.
Mm. Yeah, that's a very good point. But my gut feeling is that we're not close enough to be 5, 10 years where you can do. Maybe for see what the problem is that lean is on the million line range, and it's million lines in several specific fields, especially in arithmetic geometry, because Kevin is there, so he led a big thing. Lean doesn't have uh, anywhere close to sufficient data for other fields. In finite group theory, for example, it has very little. And in mathematical physics, it has very little. In algebraic geometry, it's beginning to catch up a little bit. I just the general feeling in the lean community is that once we have reached it's kind of a more uniformly distributed things across all branches of mathematics, and we reach the billion line range, then we can train an auto-formalizer to fill them in. And okay, the auto-formalizer would then be checked so that at least we have a good database. So the current database of Lean is it's not at all uniformly distributed in all of mathematics. It's just a little peaks in certain little esoteric areas. And to reach the AlphaZero stage, we need a large uniform scan of the landscape of mathematics. And that could take decades because we need people to type things in. It's quite remarkable we've reached this stage in 10 years, and this is essentially 10 years of humans typing in a total about a million or so lines of lean code. Uh, and so, but once we get there, I think that the hope is certainly in the future. I can't. It's hard to put a scale on this. Is to let it play this AlphaZero game, and I think maybe even more importantly is is ultimately to replace peer review in the sense that if you write a paper, formalize it into lean, and if you check it, there's nothing more to check. The peer review process will then just be a judgment of how important the paper is, not how correct it is.